have Rajat Mittal from nearby Rutgers talking today.
Great. Thanks, Russell, for letting me an opportunity to talk. This is joint work with Troy and Mario, and the title is Product Rules in Semidefinite Programming. So today what we are going to see is kind of find out conditions under which nice semidefinite programs multiply. So I will explain what kind of semidefinite programs we are looking at and what do I mean when I say that they multiply well. So that will be the focus. So let's start with some motivation. So in complexity, one of the nice problem is, well-studied problem is independent set. So in the independent set, you are given some graph, and you want to find a subset of vertices such that no two vertices are connected in that subset, right? So you want to find a subset of V such that for all Vi, Vj element of S, Vi comma Vj is not any, right? So this is a simple problem. Let's try to write it as an integer program. So I can write it as, and the problem is to find the maximum subset which satisfies this condition, right? So let's say I assign every vertex either 0 or 1. Okay, so I can say that I want to maximize this sum such that xi times xj is equal to 0 for all ij element of E. Right? So this is a simple integer program which finds out the value of the maximum independent set. And I can, just to make it quadratic, I can write it like this. And this will just find out the square of the independent set instead of the size of the independent set. So this is hard to solve. So what we do is relax it to a vector program, and we can write another program. We can say maximize. Okay. So this is all ones matrix taking dot product with x. So now my xij is xi times xj. So this is all, this has been done a lot of times, I guess, and normalization condition, and then xj ij is equal to 0 if ij is element of E, right? So this one matrix is 1 1 1 1 matrix. Okay, so this represents this if this is of this form. We can say that instead of xi element of 0 1, these are vectors, and then this becomes Loa's. Sorry?
Sum of the squares of all xi.
Right.
Is that 1?
So this is just a normalization, right?
Okay.
So you can normalize it anyway, it doesn't matter, but this will just normalize the vectors. So okay, so so this is also known as Loa's theta number. So so this is one instance where semidefinite programming. So this is a semidefinite program. So this is one instance where semidefinite program.
Semidefinite if you put in the constraint that x is semidefinite.
Sorry, yeah. So so instead of this, I will get this constraint. Wait. So that just says that there exist vectors Vi and Vj such that I can construct this matrix X. Xij is dot product of Vi dot Vj. So
so see, in terms of the dot products, what are the different constraints give you? So the xij equals 0 is that Vi dot Vj is 0.
right.
The trace, so is just the sum of all the entries in X.
Right.
And then still the trace, okay, it's normalized. You can normalize it any way you want, but you
Right.
would think that you normalize it to n.
You can do that. Like it's just that here you will multiply the objective value by a normalization factor. So but
with trace equal to 1, you basically divided the entire matrix by the size of the independent set, whatever it was, because the trace would have been the size of the independent
exactly.
set. So now the objective function, instead of being the square of the size, is actually equal to the size.
Right.
On the response will take
So-
the condition that it is between 0 and 1.
I'm sorry?
No. So no.
Okay, but it's a strange. Okay, why not just say that the diagonal is 1? Is the all 1 vector? So let's say that each vector is of length 1.
No, but he wants each vector to be of length
Between 0 and 1, 0 and 1.
square.
Some of the vectors, right? So that
Ideally, some of them are 0 and some
so
of them are
like this solution won't satisfy that, right?
Okay.
This is not a plus minus 1 program, just as
The 0-1 program.
Okay.
So this is not like
But, so then, why not? Why isn't it that the trace is less than or equal to 1 rather than?
so as like Madhur said, like once you make this condition, then instead of square, this value will be exactly the independent set size. Trace will generally, so in this case, the trace will be the size of the independent set. If you take this, then the trace will be size of independent set,
Right.
and this is square of independent set. So by this normalization, so
Okay.
so you can get anything times it.
Okay.
I think this is like
it's one of the relaxation.
one of the relaxations, right? And so I just wanted to say this one because this is what Lowas uses for the theta number. So this is the
Okay.
theta number. But okay, so anyway, so this was used, and this is used for Shannon capacity also. So I will, and similarly there are things called non-local games. So in non-local games, you have a prover. You have two you have two provers and one verifier. And the verifier asks questions S from some set T, and they are supposed to reply. Actually, I will later use some other notation. So the verifier asks questions S and T from the prover 1, prover 2, and prover 1 and prover 2 reply with U and W respectively. So this is, and they and verifier needs to find something like, let's say, coloring of a odd cycle. So 1, 2, 3. So suppose provers want to prove that this is properly colored. So in that case, the verifier can ask either give me the color of this vertex from prover 1 and this vertex from prover 2, or it can give the same vertex to both the provers and ask what is the color, and he just checks respectively whether the coloring is consistent. So this is a non-local game, and one variation in the quantum version, we allow the provers to share entanglement also, and then ask whether they can do better, and it seems they can do better. So semi-definite programming is nicer in this framework because for XOR games, when U and W are binary and the predicate just depends upon the XOR of U and W, we can give the value of this game exactly as a semi-definite program. So actually, verifier looks at W and output 1 or 0 depending upon whether it is satisfied or not, and so So this is the semi-definite program corresponding to this prover game. Still, again, it has this framework. Okay, so this notation means dot product between these two matrices. Okay, so A dot B is just summation over ij aij times bij. Okay, so this is once again another semi-definite program, and the nice thing about quantum XOR binary games is that this exactly specifies the value of the game.
What would A be?
Huh? A will be a function of verifier. It is like -1 to the f XOR, but it will be a function of this. So these are the two instances when semi-definite program was used, and both these cases, the product of semi-definite program was also useful. Sorry, E is like all ones vector. So this is like the last and all the diagonal should be 1. So for all I.
So now the matrix corresponds to as sort of has S times U rows and T times W columns, and entry corresponds to the sign of the XOR of the two axes.
It will. So this is a particular case when I'm considering only binary XOR games. So it's just this matrix is S times T, but in the general case when U and W belong to a set, this will be big, and I will come to that. I will explain it later. So this is binary games, and that's why this is slightly more simple.
We are assuming that S is equal to T for now?
S is equal to T?
Oh, A is S times T.
A is. So yeah, so right. So the general matrix will be used when we prove Feigelova's STP multiplies. So that will come later. But so okay. So in both these cases, these SDPs are useful because they further prove that these SDPs multiply well. What I mean is that if suppose so let G be the graph here, and this is, let's say, alpha G, then
You want to use theta probably because alpha is standard independent.
so right, okay, so I will use the same thing there also. So okay, so let's say theta G and theta G times theta G, and similarly here also for parallel repetition of the games. So now if G is a game, then value of parallel repeated game is Vg times Vg. So a perfect parallel repetition theorem holds for non-local games. So in both of these, this multiplication property is useful. So today the motive of the talk is to consider a general semi-definite programming, define what the product means, and see under what conditions this multiplicative property holds. Okay, so so let's see. So okay, so let's look at a semi-definite program. So the program we consider is, so now J is the objective matrix. Then this is A constraint matrix, and then the condition that X is positive semi-definite. So A here actually is a list of constraints. So A is actually equal to this list, and each one of these has the same dimension as X. So this is like a list of constraints which says that AI dot X is equal to BI. So this is a general semi-definite program. So now given this general semi-definite program, this program is specified by 3 parameters, J, A, and B, right? So and so you'll define the product of two semi-definite programs to be, so suppose there are two instances, J1, A1, B1, and J2, A2, B2. Okay, and the product of two semi-definite instances is so this defines a new semi-definite program. Okay, so one of the thing here is that okay, so if there were M1 constraints here and M2 constraints here, this is list of all M1, M2 constraints. Okay, so every constraint is multiplied by every other constraint. So, so this seems to be a nice definition of product of two semi-definite programs, because we see in all these instances this this kind of takes care of all these semi-definite cases. Okay, so this seems like the natural product of two semi-definite programs, but there can be other definitions of product also.
Can you go through and try to like decompress this a little, you know, to decipher this? So what does this actually mean? So you have n1 variables for the first constraint and n2 variables.
So
intuitively, you know, so the matrix of dimension n1 by n1.
okay.
N2 by n2, and now.
Right. So let me write the dimensions of these. So I will. So my matrices will be square and symmetric. So X is n by n, and since I'm defining this dot product, J is also n by n. Okay. All AIs will also be n by n. So what I'm saying is that this defines M constraints.
So this product is only defined if the two semi-definite programs have matrices of the same dimension, or they can have matrices of different dimensions.
Tensors is any dimension.
Any dimension.
So could be more general in one and
Right. But in generally it is useful when actually these programs are of the same kind. But yeah, this definition is defined for different dimensions also.
So given the way we've defined RSDP, so it easily implies that for the product SDP, your objective value is at least higher.
Exactly. Exactly. So the question is, when is it equal? Okay.
No. So explain more. So the in the product, so you know, say that both of them involved n variables, you know, where n by n, then the tensor will be n squared by n squared.
Right.
So then, you know, how do you, so you have one vector for every pair of vector in the original, so one variable for every pair of variables, and then the objective. So let's see, how does, so okay, so I guess intuitively you could let, you know, so for a vector, I guess intuitive. Actually, I'm still confused.
So okay. So is the definition clear and product is
No.
Okay.
I mean, just how it works is not clear. So, what it means intuitively.
Yeah.
So, J1 tensor J2 is going to be an n squared dimensional matrix. So you think of each, you know, so, okay, what's the product solution? Say you've got a solution to J1 and a solution to J2.
Just like
What's
tensor.
the product solution?
Just the tensor.
Vector by vector tensor.
Okay.
And that's one candidate.
One candidate solution.
Um,
I think that maybe one way to think about it is not think about X as a matrix. X is just a vector, J is just a vector, and K are just vectors. So you ignore the fact that it's a matrix.
I don't know.
And
if
then
that
you
helps.
intercept it. What?
I don't think that helps. Because
So I will try to explain why it
Right.
helps.
Okay.
And you ignore the semi-definite condition, which is just the intersection with some convex body that helps later.
Yeah.
So let's ignore the semi-definite. So there are just linear conditions, two sets of linear conditions, and the new conditions are the tensor of the previous linear conditions. So you should you should satisfy all of them.
No, so how is that satisfying all of them?
Because you take every possible tensor product.
Yeah.
Maybe it's helpful to write down the
Yeah,
square of the
maybe.
game you have on the left. Like the square of this and this, which is able to AM, right?
Right.
Just write down the square of the semi-definite program.
Okay,
So
so
if you look at one new constraint times the product of the two initial solutions, it splits into the product. The dot product splits into the product of the two dot products. And that which is equal to the right hand side.
so sorry. Like so this has m1 choices and this has m2 choices. So initially you had m1 constraints for first instance, call it pi 1, and for pi 2 you had m2 constraints, and now you take every possible tensor product, and say that this is also a constraint.
Right. But what is?
Now, if x1 was the solution to the first game, x2 was the solution to the second game, then the matrix x1 tensor
So x2 is a solution of this.
Yeah. But. Okay. So let's say we go back to independent set. Okay. So you're saying, okay, say we have, so there you think of if you have an independent set of size m, or say k1, and an independent set of size k2, then you take you're looking in the product graph and you look at the product of those two independent sets. So that's the tensor product of those two vectors, and has size n1, n2. And now the constraint is you can't have both of
Both of them
product
as
these
edges.
two is 0, and the product of these, when you have an edge in one graph and an edge in the other graph, then you have the constraint that so
Both of them are not an edge. So the new vertices will be, let's call a1, b1 and a2, b2.
yeah.
And in the graph, the constraints will be that both of them cannot have edges. So this was not connected, this was not connected.
Okay. So
So that will,
the corresponding product graph is to put an edge if there are both edges.
right,
Okay.
the strong product. Okay, so this product definition is okay. So this is the product definition, and now the objective is to see. So we want to give conditions on these 3 parameters, such that let's say if pi1 was the first instance, and I suppose say v is the value of the instance, then v pi1 tensor. So this denotes the value of the first semi-definite instance. This denotes the value of the second semi-definite instance, and we want to find conditions on this such that this holds.
So first, is there an example where it doesn't hold?
Sorry?
You know an example? Is there a natural example where it doesn't hold?
Yeah, you can take linear programs, and linear programs are a special case of semi-definite programs.
Okay.
So linear programs, like if all the entries are not positive, then that doesn't hold. Or okay, let's take a.
Even in independent set, if you just consider the linear program, it's only larger, and in many cases, it's strictly larger.
It's strictly larger. There are many cases. You can take the maximum eigenvalue, and when you multiply, like you can construct a matrix whose maximum eigenvalue is -2, but the square when you take it will be 4. So you can many programs. So anyway, so this is our task, and let's see. So in the first article, we gave 2 sufficient conditions. So one was that if J is positive semi-definite, then the product theorem holds. And the second condition was if J is anti-block diagonal and all AIs are block diagonal. So what I mean by block diagonal is this matrix, and block anti-diagonal is 0. Okay, you can have a different PQ. Okay. So this is anti-block diagonal, and this is block diagonal. So these were the 2 sufficient conditions, and we came up with a necessary condition also. But still, there were cases in semi-definite programs which we couldn't handle. And so today, I'm going to talk about those cases. So the thing which was different about those cases was that they had this inequality constraints also. So you had.
So these were sufficient.
These are sufficient.
Any one of them is sufficient to get
Right.
the product.
Right. So so they had these new constraints. In general, if given this kind of a program, you can always convert it into the previous program. But the only problem is that in those new product programs, the multiplication of these constraints was not considered. So the natural definition of product is different. So what I mean to say is that so now let's say I have 2 instances, pi1 and pi2. I have some equality constraints, some inequality constraints. Similarly for this instance. Okay. In the previous case, this constraint will be multiplied by this constraint also. But when you consider this kind of program, what you wanted was that only these were multiplied by these and these were multiplied by these. So so we basically wanted to find out, so now we can say that phi 1 is characterized by B1 B2, then so here also B is a list of constraints, okay, and now this is the product of these two semi-definite instances. And now we can ask the same question, that under what conditions on this the product theorem holds here. Okay. So actually, okay. So let's dualize this program. The dual of this is minimize sorry.
Now, what are you going to prove?
Sorry. So I will say under what conditions on this program
Okay, can you
multiply.
tell us what the theorem
Sure.
is?
So slightly involved. The conditions are, again, J is anti-block diagonal. A is block diagonal. B is anti-block diagonal. And there exist U such that U transpose beta. So J can be expressed as a linear combination of matrices in B.
Just wondering, what is an actual example for which you need this type of result?
So if you consider non-local classical games, you have these kind of constraints which say ui dot uj is greater than 0, unique games. So that is where it is utilized. Like if you write unique games STP, you will have these kind of constraints.
Here, all of them must simultaneously hold to get a product.
Right. So this is the, so if this holds, then the okay, so
I didn't get the last one. So it says J, there exists a U such that J is U transpose B.
this is summation over I ui b b. So this is a list of matrices, right? So this is what I mean by this notation.
That's a very strong constraint.
Yeah, that's the whole problem. So if you see the previous thing, there was no condition like this.
Right.
And I will show you a counter example that when this condition doesn't hold, the product theorem doesn't apply. So either this condition is there or there should be something like this. So it cannot be removed. So with these three, it doesn't hold. So we know that. So this is some other form of this, or this is required. So that we know. Okay.
This is just saying that J lies in the cone of matrices and B is coming from the dual sum of.
Right. So this is the dual program of this primal. Sorry?
The independent set example is covered by your...
Independent set is covered by the previous condition set. So this actually, there is a product theorem about discrepancy. So you relax discrepancy to something called gamma to infinity, and then gamma to infinity is a semidefinite program, and that perfectly products. So that actually comes through this, and the original Feigelova's thing also comes through this. So I will explain. So there are other examples which characterize this.
I mean, if I write the sort of SDP, which would be the most obvious one for independent set coming from this, which is just maximize summation xi square, xi dot xj is equal to 0 and xi is between 0 and 1. If I just translate that to semi-definite programs,
Right.
then it will be covered by a second formalism, right? Because the cost function will be the identity matrix. You're looking at summation xi square.
It should be anti-block diagonal. It shouldn't be
Oh, it's anti-block diagonal.
diagonal,
Oh.
not block diagonal.
Oh, so that is not covered.
The other one, like the one I wrote,
Yeah, and it's the one here.
Yeah.
Okay.
it actually will be covered by J positive semidefinite, the other condition, not the anti-block diagonal thing.
Yeah, and I was trying to put it in
Okay.
this framework, the one with inequalities for 0 and 1.
So, but you don't have any condition here, just that J is, if J is.
No, that's very surprising actually, because it seemed like J positive semidefinite seems like a very obvious condition, but it seems that doesn't work here. We don't have a counterexample. No, we don't know what happens when J is positive semidefinite. Okay, so let's see. So what will be our proof strategy? Our proof strategy will be, so you have this value, and you know that this is greater than this is true because if you just take x tensored x1 tensored x2, that will be a solution of this program. So that shows this. Okay, if we can show a similar thing about the dual, so I will denote the dual by star, and sorry, star. So if I can show something like this, and if I assume that duality holds, so I have to assume here something, because in linear programs we know that duality is given, so the value of the primal is equal to value of dual. In semi-definite program it's not always true, but under very mild conditions you can say that strong duality holds. That means the value of the primal is equal to value of dual. So here we will always assume that strong duality holds. If that is the case, then this is equal to this, and then this, so this will be basically equal to star. So this you can convince yourself, but then if this is the case, then everything will be equal. Okay, so what we need to show is that if y and z are a solution of, so if y1 comma z1 is a solution of pi 1 and y2 comma z2 is a solution of pi 2, and if I can show, sorry, thank you, is a solution of this, then I'm done, right? Small caveat here, we can't show this, but what we can show is that y1 tensored y2, and there exists some other vector v which is a solution of this. And this still works because the objective function does not depend upon z. So, so our task will be to show that y1 tends at y2 and there exists a vector v such that it is a solution of pi1 star pi2 star. Okay, if we can show that, then the product theorem will hold.
So you're really using the fact that right hand side is 0 in there.
Exactly. So I think one of the nice thing about this is that as I go through the proof, we can sort of see what programs will multiply and what programs will not. Why does this anti-block diagonal, where anti-block diagonality should be there, where block diagonality should be there, and these things will kind of be clear. So, and yeah, exactly. So we need this 0 to make it work. Okay, so let's see. So we are given this, okay? Assume that okay, and similarly for y2. So if this is true, then the product theorem will hold. And I will show that given those conditions and this, we know this, right? And given those conditions, this will hold. So once this holds, then the product theorem will hold. So let me prove that. Assuming this, the product theorem will hold. Like I will find these vectors which are a feasible solution of pi1 star times pi2 star. Okay, so So I know that all these 4 matrices are positive semi-definite. So by the property of semi-definite cone, this entire thing will be positive semi-definite. Okay, and then this will be equal to so these are big matrices, and once you do the calculation, you can see that all these are equal. So this is equal to this, and now if I look at this, so now we use the condition that J can be written as a positive combination of B's, and then we can change this into positive semi-definite, and here V will be equal to okay. So with this substitution, this will hold, and this is the exact dual feasibility condition for this thing, and because u1 and u2 are positive, V is also positive. Okay. So this shows that product theorem holds. So now I just need to prove this. Can I erase this? Like this this is just calculation. So this is given to me, okay, plus j. So by the properties, this matrix is also block diagonal, and this matrix is anti-block diagonal. Okay. So, and if I consider this matrix, so it's you can say that there are two matrices P minus Q. We are given that this is true, and we want to prove this is true. So this is P and this is Q. P is given to me as block diagonal, Q is given to me as anti-block diagonal. Okay, and if x1, x2 is an eigenvector of this matrix with some eigenvalue, x1 minus x2 will be an eigenvector of this with the same eigenvalue. So once you write it, you will see. So that just uses that P is block diagonal and Q is anti-block diagonal. Then their eigenvectors are the same. Like they have this relation and eigenvalues are same. So that means this implies this. So both of these conditions are true. Okay, so let me give you a counterexample of the case when this is not true, all these are true, and still the product theorem will not be valid. Okay, so times x, let me. So this is just trace of x is equal to 1. Okay, so then this matrix cannot be written as a positive combination of this. So if you look at this, this will have value 0. So the best solution is when the anti-diagonal entries are 0. That is the best solution for this, and the value will be 0. But if you take the square, then on the anti-diagonal you will get once, and so you can set those entries so that this program has a positive entry. So this satisfies all the conditions except the last condition, and the product theorem does not hold in this case. So we need some other condition, except these three to have the product theorem. So, so the proof works. The other things to consider here is that actually this okay. So so from the proof, we can see actually that this need not be equality. So if this was, let's say, this also, then also our product theorem will work. The only conditions we will need is that this thing is positive, because now we have to see that the primal solution also multiplies. So the strategy was to say that the primal solution multiplies as well as dual solution multiplies. When this is equality, the primal solution multiplies comes for free. But when this is the case, the dual thing will still hold. In the primal, you have to check whether the primal solution multiplies. But these things will hold.
Then
So
you would need BIs are positive.
yeah, these are positive and these are also like the feasible solution. For the feasible solution,
Right.
if A1 is less than B, A2 is less than
Right.
B2. So so basically, if there are two set of constraints, one should be block diagonal, one should be block diagonal. So this general framework, the product theorems will hold. And tweak. So actually, I will just take the example of Feige Lovash. So they showed that the SDP for non-local games product. So I will just say so their SDP was maximize x so remember that you had two provers, one verifier. They ask question S and T, and they reply with U and W. And S was in capital S, U was in capital U, W was in capital W, so on. So So you will see that all these inequality constraints are actually made block diagonal, and all the greater than equal to signs are actually made anti-block diagonal, and then the product theorem holds. So So all these are block diagonal. So my matrix will be look like this. So S S T T, and this will have U1, U2, all the answers. So this will be the structure of my matrix. So as you said, right? So you have this matrix, and then all these constraints are only over this block or this block. And if you see the greater than equal to constraints, so, and here all these are anti-diagonal. The only problem here is that they have this modulus value, but for the modulus value, what you can do is you can choose every possible plus minus sign. So, so if there are t summands here, I shouldn't say t, if there are k summands here, then you can replace this one constraint by 2 to the k constraints with every possible plus minus sign, and that will have no modulus sign, that will still be valid. Those two semi-definite programs are equal, and that semi-definite program multiplies. That's why the semi-definite program also multiplies. So you can prove that low-pass Feige multiplies.
But here the inequality is right hand side which is non-zero.
Oh, so this is first kind of constraint. This is less than equal to. So Ax, and this is greater than equal to 0. So these are the two different constraints.
So once you replace one thing, does it become a positive matrix because it's an inequality?
Because
So we wanted that if we replace a dot x being equal to b instead by a dot x being at most b,
right.
and you wanted a to be a positive matrix.
So what you can show is that this semi-definite program is equal to that semi-definite program, and for this the primal multiplies, for that the dual multiplies, and since these two have value equal, then the whole thing will work. So yeah, for that one primal doesn't need not multiply, but so yeah. Okay, so yeah, so ultimate aim in this is to kind of find out conditions and give a tool set which helps people, researchers, so that they can recognize when the semi-definite program multiplies and when it doesn't. And it kind of gives an intuition how the constraint should be located and what the constraint should satisfy, when will the semi-definite program multiplies. So that was kind of the objective for this research. And so there are many holes in this, as I said. So we had a simple condition previously which said that if J is positive semi-definite, then the product theorem holds. But for this formulation, we don't have any equivalent condition. And similarly, there are other things. We don't have counterexamples for many things. And one of the other interesting direction is to see, instead of tensor product, if we take the composition of semi-definite program, and we can ask whether that multiplies. And once again, the problem will be to define what do you mean by composition of semi-definite programs, and then find the conditions.
Can you give an example of composition?
So you have in communication complexity, you have functions, right? You want to find out, so you can have like f of g of S1T1 and gm of SNTM. So like for this function, there is this communication matrix. For that, you are given discrepancy. For f, you are given discrepancy. Can you say something about this function? What is the discrepancy of that function? So yeah, these are probably the interesting open problems.